What about the rest of the chapters which are already done? Are you guys practicing questions based on that?
Yes, ma'am.
And you're able to solve it?
Yes, ma'am.
So today what we will do is, before starting off with our curriculum, we'll try to solve the frequently asked question in your paper. I've got some questions from the chapters which are already done by Vishu sir. Okay? Not anything beyond that. So we'll try to solve it together so that we know that everybody is practicing at home the chapters which are already done. Okay? So let's start off with the simplest question based on your, some basic concepts of chemistry. The number of moles of hydrogen molecules required to produce 20 moles of ammonia. 20 moles of ammonia through Haber's process. And your options are given as 20, 30, 40 and 10. Who can solve this question for me? The question is visible to everyone. The question says the number of moles of hydrogen molecules required to produce 20 moles of ammonia through Haber's process. So in order to solve this question, first thing I should know what is an Haber process is.
Ma'am, 30 moles.
What? Say that.
Answer, ma'am, 30 moles.
30 moles. So your answer is coming out to be, you're saying it is B option. Anybody else who has solved this question? Are you also getting the option B? Okay. Ankit, can you tell me what is Haber's process is?
Ma'am, in this process, 3 moles of hydrogen react with nitrogen in the presence of iron oxide as catalyst to form ammonia.
So basically, the production of ammonia with the help of hydrogen and nitrogen resulting in ammonia formation. So is this my balanced equation?
No, ma'am.
No. So I need to balance this. In order to balance this, what will I do?
Ma'am, 3 hydrogen, 2 ammonia.
So this is how I balance it. So now I can see there is 2 nitrogen present on either side and 6 hydrogen present on the both the side. So from this equation, what can I say? In the terms of stoichiometry, of blood stoichiometry, right? So what can I infer from this equation? So this is my Haber's process. So what can I infer from this? What are the inferences I can make from this?
3 moles of hydrogen are required to form 2 moles of ammonia.
So basically what I can infer is that 3 mole of hydrogen will react with 1 mole of nitrogen to produce how much? 2 moles of ammonia. right? That is what I infer from the equation. So what is given? I have been given number of moles of hydrogen molecule. That is what I need to take out. So I need to take out number of moles of hydrogen molecule. So that means this I need to find out. And what is given to me? It's given that it produces 20 moles of ammonia. That means 20 moles have been created for the ammonia. So how much of hydrogen is required? That is the question which is being asked. So I can see from this equation 3 mole of hydrogen will produce 2 moles of ammonia. Everybody is clear about that? What about the rest of the class? I'm getting only one response. Reshma, Surbhi. So what is happening? So X mole of hydrogen will produce 20 mole of ammonia. That is what I meant. So when I do the cross multiplication, the elementary method, what will I get? X equal to 20 into 3 upon 2, which comes out to be 30 mole of hydrogen. That is what the answer is. Clear? So if the stoichiometry chapter is clear to you, this question is the most simplest you can get from the some basic concepts of chemistry, and it has been asked in 2019. Okay?
Yes.
So let's try another question. 4D, 5P, 5F and 6D. These 4 atomic orbitals are given to you and you need to arrange them in decreasing order. Arrange them in decreasing order, and decreasing order of their energy. And the options given to you are 6p, 5f, 5p and 4d, 6p, 5f, 4d, 5p, 5f, 6p, 4d, 5p and 5f, 6p, 5p and 4d. Which one will be the correct answer and how did you deduce the answer? So it is being given 4 different atomic orbitals are given and you have been asked to arrange them in decreasing order of their energy, and 4 different options are given to you. How do you calculate it?
Ma'am, in the question there is 6D, ma'am, but in options there is 6D nowhere.
Okay, it is 6p then. I'm sorry. Clear? 6p. My mistake. 6p. So what?
I'm option C.
Option C. Anybody else? Option D. Reshma is saying option D. Anybody else? So how do you determine the increasing order of the atomic orbitals? What is the rule which is followed or principle which is followed? n plus 1 rule. Okay. What is that n plus
1 rule.
What is the n plus 1 rule states?
The shell that is having the more n plus n value will have the more energy.
Okay. So when you answered, Ankit, the option C, 4D and 5P. Can you see? It's saying 5P is of lower energy than 4D. Is it correct? Is it correct? N plus 1 rule, when you are going to apply it, is it going to be correct? 4D is greater in energy than 5P? Reshma, can you explain why D is the option? Like, how did you deduce it? How is your answer different than Ankit? So the n value is more, right? So Ankit, see what mistake you have done. 5, 4. So obviously this has to be this side. Then only it would be a right answer. 5F, 6P, that is fine. Then it would be 5P, then 4D. If you are not able to apply the n plus 1 rule, you can even look for Afabua principle. What is Afabua principle? 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, and 5f, 6s, 6p, 6p, 7s. So when I see 1s would be, then it would be 2s, then 2p, 3s, then 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s. Right? This is how we used to do the Afabua principle. So where does 4D comes? 4D is coming below 5P. Can you see?
Yes, ma'am.
So that's where you went wrong, and the option C is wrong. Option D is the right answer. Clear?
Yes, ma'am.
Fine. Let's see another example. Which of the following diatomic molecule species has only pi bonds according to MO, and the options given are N2, C2, BE2 and O2. Sorry, diatomic, right? O2. So I need to determine which of them has only pi bond according to MOT? What will be the answer? MOT, you understand? Molecular
C2.
C2. Okay, molecular orbital theory. Right? So Ankit is saying C2. Anybody else? Reshma is also saying option B. Shanmuga is also saying option B. Okay. What is the electronic configuration of C2? MOT point of view. What is the electronic configuration?
Sigma 1s2.
Yes.
Sigma star 1s2.
Yes. Sigma star 1s2. Then
Sigma 2s2.
sigma 2s2.
Sigma star 2s2.
Yes. Then
Pi 2px2. Pi 2py2.
2px2 and pi 2py2. Are you all agreeing with this electronic configuration?
Yes, ma'am.
Yes, ma'am.
So, as I can see, only pi orbitals are present. That is what it has been asked. Only pi bond. What will be the electronic configuration of O2? How O2 orbitals are different than your C2? What will be the electronic configuration in the case of O2?
Sigma 1s2. Sigma star 1s2.
Sigma 2.
Sigma 2s2. Sigma star 2s2.
Then
Sigma 2pz2.
sigma 2pz2. Then
Pi 2px2 equal to pi 2py2.
fine.
Pi star 2px1. Pi star 2py1.
So what is the difference between C2 and O2? In C2, these pi 2px and 2py are in lower energy, whereas in the O2 molecule, sigma 2pz is in the lower energy, so that gets filled first, right? That is the difference. So how will it be different than electronic configuration of N2?
Sigma 1s2.
So I'm not writing, I'm just doing ditto, okay? Then,
Sigma star 2s2. Pi 2px2.
so after this, the change arises pi 2px2, then
Pi 2py2.
pi 2py2,
Sigma 2pz2.
sigma 2pz2. So why this was not your answer? Because of the presence of sigma 2pz squared, right? That option was ruled out due to this. Now, Ne2, does it exist or does it doesn't exist? Does it exist in nature? If yes, how? If not, why?
No, ma'am.
It does not exist.
No, ma'am.
Okay. Why it does not exist?
Ma'am, bond order is 0.
Bond order is 0. So the bond order, how do you calculate bond order for any molecule?
Half into NB minus.
So number of electrons in the bonding atomic molecular orbital minus number of electrons in anti-bonding molecular orbital. What is NB? Number of electrons present in bonding molecular orbital. Number of electron present in anti-bonding molecular orbital. Clear? So, you have heard about thermal stability?
Yes, ma'am.
Thermal stability of the following is in the order. Choose the correct one. Choose the correct one. So the option given are H2O, H2S, H2SE, H2TE, H2PO. First option. Second option given to you is H2PO, H2TE, H2SE, H2S and H2O. C option given to you H2SE, H2TE, H2PO, H2O and H2S. H2S, H2O, H2SE, H2TE and H2PO. So which family am I talking about over here?
Chalcogons.
Yes. So the oxygen family or chalcogens. Oxygen family. So what will happen to thermal stability and what will be the order and why do you think that is your answer? Anyone? What will be the answer? I need to choose the correct order for the thermal stability.
Ma'am, B.
B, ma'am.
B. Option B, because thermal stability decreases down the group. Now, thermal stability decreases down the group, which is right: polonium, tellurium, selenium, sulfur, oxygen. That is the oxygen family: oxygen, sulfur, selenium, tellurium, and your polonium. Right? This is my oxygen family. So, when I compare the thermal stability, that is perfect. Have you heard about the rule Fajan's rule?
Yes, ma'am.
Yes. What is Fajan's rule says? What does Fajan's rule states?
Smaller the size of cation, larger the size of anion, more is the covalent character.
Yes. So what is happening actually down the group when I'm going? What is happening as per Fajan's rule?
Size is increasing.
Size is increasing. The charge is remaining the same, the size is increasing. When the size increases, what does happen? The polarizability power will decrease or increase?
Ma'am, increase.
It will increase. So that means it will try to
Covalent character increases. Thermal stability
So
decreases.
you are saying, let me put forward. So you are saying the polarizability power will increase down the group? Are you suggesting that? Think again.
Yes, ma'am.
So you mean to say polarizability of oxygen will be less in comparison to polonium? Which will hold the pair of electron more towards each other?
Ma'am, oxygen.
Oxygen will hold the electron more towards each other. And thermal stability will be defined by more of ionic character present in the bond or more of covalent character present in the bond? Which will favor thermal
Ma'am, more
stability?
ionic.
More ionic. So more ionic, how do you determine whether the compound? So let's say I am comparing water with H2PO. So which one would be more ionic in nature? Which has more ionic character in the bond? Let me put forward in that way. Or which has more covalent character in the bond?
Ma'am, please repeat.
I am asking which of them, like I am comparing H2O bond and H2PO bond. I am asking which one would be more ionic, which one will have more ionic character? Which
H2O.
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 So H2O being more ionic, that means the polarizability power of oxygen will be high or low?
Low.
Low.
So you mean to say that the electron pair which is shared between the hydrogen is going to feel less pull from oxygen.
Ma'am, that is polarization.
Polarizability power, that is for an anion. Okay, let's go via this example. You have iodine and fluorine. Which has more polarizability? I has more polarizability. Anyone who thinks that I does not have high polarizability? Can you define polarizability? Can you define polarizability to me? Can you define polarizability to me? What is polarizability? Yes, anyone? Okay, here. Anyone who can define polarizability? Reshma, Ankit, Shanmuka, Sheetal.
Ma'am, distribution of electron cloud and the anion towards cation.
Distribution of electron towards anion and cation. That's what you're trying to say?
Electron cloud in the anion towards cation.
Okay, in the anion and towards cation. So let's say if I have Hi, that means you are saying like this.
Yes, ma'am.
And in the case of HF, you are saying it will be equally distributed. Are you saying that? You're saying that, right? That is what you meant?
Yes, ma'am.
So when you're saying that, so let's say I know a molecule which is polar, NaBr and AlBr3. Which one is more ionic in nature? Which one is more ionic in nature? AlBr3. Okay, so this is more ionic. Why is it more ionic?
And because it is having less charge on the cation.
How it is determined? It is determined with the help of ionic potential. Ionic potential is charge upon radius for the cation. Right? Higher is this ionic potential, more is the ionic character. Lower is this value, less is the ionic character. Right?
Yes, sir.
So when I see in the case of sodium, the charge is +1 and the radius is small only. It's a small value in comparison to +3 and a little larger radius. So this has tendency to diffuse more. That's why it is covalent in nature in comparison to NaBr. That's why the melting point of this is more than 900, whereas AlBr3 is about 95.6, right? Due to the covalent character. Otherwise, whatever we have studied in the lower classes, what we have studied Al3 plus and Br minus. So that means both of them are cation and anion combining. So it should have been ionic, but it has more of covalent character, due to which the melting point is this low. Clear?
Yes, ma'am.
Based on the bonding, you need to match XCF4, XCF6, XCOF4 and XCO3. This is your option 1, 2, 3 and 4. And you have to match it with the second column which has given pyramidal, B option which is given square planar, C option which is given as distorted octahedral, and D option which is given as square pyramidal. So you need to match the following, that is, which shape will it have? XeF4, XeF6, XeOF4 and XeO3.
Ma'am, 1B.
So 1 with B, second
2C.
2 with C,
3A.
3 with A, and
4D.
4 with B. What about you, Shanmukha? Are you agreeing? Ankit, are you agreeing with this?
Ma'am, 4th A.
Okay, I'm getting another answer. 4th is A. Then what about the rest of them? So that means you're saying 3rd with D.
Yes, ma'am, 3rd with D.
Okay. And rest of the both of them are same option for you as well, or different?
Ma'am, same.
Same. Anybody else who is getting a different answer than this? So 1 is B. So that means, let's see, one by one. XeF4. Xenon has 8 electrons in its outermost orbit. 4 are involved in bonding and 2 set of lone pair. So that means the number of hybridization comes out to be 6. 6 is octahedral in geometry. Shape would be, the lone pair will occupy the axial position. It would be square planar. Right? This has 0 doubt. 1 is B. What about second is C, you are saying. So XeF6. So similarly, I have 8 electrons. 6 are involved in the bonding, 1 set of lone pair. That means it comes out to be 7. 7 is what geometry?
sp3d3.
sp3d3. Geometry would be, what is the molecule?
Octahedral.
Say that again, please.
Octahedral.
Octahedral. 6 is octahedral. We have seen it here. See? 7 will correspond to
pentagonal bipyramidal.
exactly. It would be pentagonal bipyramidal. This will be my geometry. But there is 1 set of lone pair present. That is why it comes out to be distorted octahedral. Clear? So this option is also right. Now there is a confusion between 3rd and 4th. 3rd is XeOF4. XeOF4. So in this case, 1, 2, 3, 4, 5, 6, 7, 8. Double bond to the O and fluor Fe. So that means 1, 2, 3, 4, 5, 6. 6 is the number I am going to get over here. 6 is octahedral. and out of which one will be occupied by the lone pair, the A shell, so it becomes square pyramidal. It becomes square pyramidal. Clear? So which one is right? Third with D. Now fourth with A, that is pyramidal structure. I'm doing it over here. XCO3, that means 8 electrons. So each one of them will form a double bond with it. So that means the number comes out to be 4. Tetrahedral geometry, shape would be pyramidal. Is it clear, Reshma? You got that wrong, right?
Ma'am, Shanmukha.
Shanmukha. Okay, I'm sorry. Shanmukha. You got. Now you understood what is the mistake you made?
Yes, ma'am.
Yes. So
Yes, ma'am.
don't make this mistake. Okay. So, and this question has been asked about like every alternate year. Okay. Same value, same number, even the options are same. Okay. So this question has been asked every alternate year. So now proceeding further with our chapter. We stopped yesterday at electron displacement, right? And after that, what I'm going to start off, what are the representation? Representation of structures in different manner. In different manner. What are the ways I can represent a structure? What are the different ways I can represent the structure? Have you heard about bond line structure, condensed structure, open chain structure? Have you heard about them?
Yes, ma'am.
So, there are 3 ways of representation. One is complete, another one is condensed, and the third one is bond line structure. Right? So now let's see each one of them in detail. What happens in this? So let's say I am taking pentane. Pentane is an alkane with the 5 carbon, that is C5H12. Right? The complete structure would look like how? That I draw every carbon and represent all the bonding which is present with it. So, second carbon, third carbon, fourth carbon and fifth carbon. This is how the complete representation of structure occurs. But what happens in the case when I try to condense it?
Ma'am, an alkane chain is considered as a chain only, and the points of the chain are considered as CH3 or carbon.
So, in the condensed form, it would be written like this. Can I write it like this? This is my condensed form with no bond representation in between. Whereas in the bond line structure, the carbon represented by line 1, 2, 3, 4, 5, and you do not represent hydrogen over here. Clear? The complete structure,
Yes, ma'am.
condensed structure, bond line structure. So let's say I introduce a variation. What do I introduce? Let's say I give you 2-pentanol. So 2-pentanol, when I draw the open structure, it would look like at the second position I am going to have an OH group. Rest of the structure remaining the same. In the condensed structure, what would happen? How will this OH be represented?
Inside bracket.
Yes. So CH3, CH, OH. I'm sorry, I have represented CH, OH, CH2, CH2, CH. What about the bond line structure? How will that be represented?
Ma'am, on the second point, our OH bond is being presented.
Yes. So at this, the OH bond. So the functional groups are represented on the bond line structure. Clear? So if let's say if I have a multiple bond, that is a double bond or a triple bond. So I've been given two chloro pent 2E. Okay, this is the name. So when I draw the open structure, 5 carbon. After that 5 carbon, on the second carbon, there is a double bond. So let's say this is 3. 4. Okay, 4. And on the 1, 2, 3, 4, 5. And on the 4th carbon, there is a chloro group. Rest of them as hydrogen. How will I write the condensed structure in the case of multiple bond present? How will I represent a multiple bond with the help of a condensed structure? How will this look like in condensed form? Anyone?
Ma'am, double bond can be used.
Double bond will be
Yes, ma'am, double bond will be used.
so that means CH3, CH, double bond CH, then your CH, Cl, and then CH, Cl, and then CH3. This will be the case in the condensed form. What happens in the bond line structure then? What will happen in the case of bond line structure?
Ma'am, bond line will be drawn below the bond, single bond.
So I have 5 carbon like this. After the 5 carbon, on the second there is a double bond, and on the 4th there is a chloro group. Fine. So let's say I have been given another molecule like this. This is an alkyne molecule. So how will I represent it in bond line structure? How is the triple bond represented?
One will be below the main bond and one will be above the main bond.
So remember, the triple bonds are linear in shape, right? So they do not come as like if you are drawing it like this, then the next bond will go like this, because this has to be linear. So when I am drawing the bond line structure, I will draw like this. Am I being clear? It will be lying in the plane. You cannot do it like this. So this cannot be done. This cannot be done. This is wrong. In the case of triple bond, you cannot do this. What you can do is this. Clear? This is the wrong way.
Yes, ma'am.
This is the wrong way of representation. Wrong way. What is the correct way? This is the correct way. So let's say I have different types of functional group. CH3, CHCl, CHOH, CHO. How will I draw the bond line structure for this? How will I draw the bond line structure for this? Can you draw the bond line structure for these?
Ma'am, in the first question and second carbon there will be a chlorine and one carbon of two.
Right. After this,
Ma'am, at fourth carbon there will be a double bond O.
there will be
Above
double
or
bond
below.
O and an H. Right? This is how will it look like.
Yes, ma'am.
I can even represent this in this manner as well. I do not represent H. I can do that.
Yes, ma'am.
What about the next part? CH3, CH2, CH2, CO, CH3. How will this look like?
Ma'am, at fourth carbon simply a double bond O.
So 1, 2, 3, 4, fourth carbon, there is double bond O, right?
Yes, ma'am.
How will I represent this?
Ma'am, at third position NH will come and the simply only a 9 will be represented.
So that means 1, 2, at the third position nitrogen is present along with your CH3, and you will be representing the H as well because nitrogen bonding you need to show it completely. Clear?
Yes, ma'am.
Proceeding further, we have already seen the hybridization in the case of alkane, that is, it is sp3 hybridized, right? If I take the simplest molecule CH4 and I did the derivation of its hybridization in the chapter chemical bonding, remember? Where
Yes,
atomic
ma'am.
orbitals combine together to form hybrid orbital. So the carbon electronic configuration is 1s2, 2s2, 2p2. So that means the orbitals which are going to take part 2s and 2p. Right? So that means in order to make CH4 4, this electron need to be excited and all of them will be used to form sp3 hybridized. When I do the sp3 hybridized, it's in the tetrahedral shape. So this is your px, py and pz. So when they combine, so atomic orbitals combine to form hybrid orbitals. So I am representing the p orbitals by red. So this is one lobe, this is second lobe, and this is your third lobe. And it will be combining with your s orbital. This will in turn return you the sp3 hybridized, that is right. It is represented like this in the tetrahedral manner, which will be bonded sigma with the overlap of the s orbital of hydrogen, resulting in tetrahedral structure. Right? This is how it happens. Similarly, for the ethane molecule as well, I can have a similar kind of a pictorial representation, that is C2H6. So the carbon will be like this, bonded to hydrogen, and one CC bond is formed. So both the carbon are sp3 hybridized over here along with hydrogen C2H6. Right? This is how it is formed. Clear? In the case of ethene, alkenes, the hybridization is sp2 hybridized. When I see the example for sp2 hybridized, C2H4. So the carbon electronic configuration 1s2, 2s2, 2p2. So the 2s orbital, the 2p orbital. So what is happening? sp2 hybridization, that means these orbitals will be mixing together. When these orbitals are mixing, that means so the two lobes in the direction px, py along with an s, this will result in trigonal planar geometry, right? Remember? So trigonal planar will look like this. This is my sp2 hybridized orbital. Yes? No? Anybody who has a doubt? So when I see the alkene C2H4 structure, how will it look like? It will have and these will be bonded with hydrogen, but I need to accommodate those, what you call that, pi bond as well. For that, what would happen? This would interact with one another, resulting in a pi bond, right? Clear? And in the case of alkynes, what happens? It is sp hybridized. What it is? It is sp hybridized. So that means only S and P is going to form a hybrid orbital. When these two form hybrid orbital, what would happen? So it will lead to a linear structure which is bonded to your hydrogen like this, and there is two set of pi bonds which are present. How are they present? These are the two different axes. So they will interact, resulting in a pi bond structure, that is C triple bonded C with an H attached. Clear?
Yes, ma'am.
So proceeding further, there are further classification which is done. Classification. What are the basis of this classification done? An organic compound has been further classified as two broad categories. What are these? Acyclic or open chain compound, whereas cyclic or ring compounds, right? Acyclic open chain compounds, the one which is lying continuously, that the CC bond are getting formed. So like in the case of soaps and detergent, it consists of C17, C18, C21 for that matter. Okay, number of carbons joined together. So those fall under the category of acyclic or open chain. Now we come to the cyclic or the ring one. Cyclic or the ring one has been further classified into two categories. What are those two categories? We have studied these two categories.
Aromatic and alicyclic.
Yes, alicyclic and aromatic. Perfect. So, what do I understand by alicyclic? This means there is ring structure which is present, but it is not aromatic. Now comes the phenomena aromatic. So there is a new term which is being introduced, aromatic. Aromatic are the class of compound which has been defined on the basis that it follows the 4 rule stated, and especially it follows Huckel's rule. So if a cyclic compound follows those 4 rules, then that compound is referred as aromatic. How does the origin of this aromatic compound came into the picture? Aromatic, the word aroma, that is the one which are used in perfume industry. So earlier these compounds were found organically in nature, stating that these compound had a nice aroma to it. That is, it felt nice when you smell that. So that's why it find its maximum application in the perfume industry. So then they classified these set of compounds possessing that fragrance as aromatic compound, and they found out there are certain rules to be followed. What are those rules? Aromatic, in order
It must have planar.
Yeah, it must be a planar molecule. It must be a cyclic system. It must have conjugated pi electron system, and fourthly, it should follow Huckel's rule. So many questions comes from this aromaticity stating which of the following is aromatic, which of the following is not aromatic, which one of the following is anti-aromatic. Okay, something like these type of questions. So when we are going to solve those questions, we need to take into the account these 4 rules. In order for a compound to be aromatic, it need to be planar in structure, and you know the double bonds present generally planar structures, like we saw it in sp2 hybridization. And one of the famous example of aromatic compound is C6H6, that is your benzene ring. Right? Remember?
Yes, ma'am.
Yes. So what can I say when I compare these 4 parameters and I see the benzene ring? What can I say? So let me just quickly see C6H6. Okay, C6H6, that means alternating double bond. Right? Alternating double bond. So this means that every carbon in this molecule is sp2 hybridized. Does anybody have a doubt that it is not an sp2 hybridized molecule? Every carbon is sp2 hybridized. So thus I can say this molecule is planar in structure. Can I say that this molecule is planar in structure? Because it is sp2 hybridized. sp2 hybridized is trigonal planar. All the bonds will be lying in the plane only. So if I see the benzene ring, this is how the single bond will look like, and the H attached to it will also be lying on the plane. The bonds which are lying above and below are the pi bonds. So that is, so if I am saying pi bond, this is your pi bond which is above and below, which is not in the plane. But as such the molecule is planar in structure. We determine the structure using the single bond which is bonded to it, right?
Yes, ma'am.
Yes. So this is planar. First condition has been met. Second condition was it should be a cyclic structure. I can see it is very well a cyclic structure. It is not breaking from anywhere. It has a continuous ring structure which is present. Right? This condition is also met. What was the third condition? It should have conjugated
pi electron.
Yes, it should have conjugated pi electron system. So now comes the theory which we have studied, resonance. So what did we study? This can be represented as, the bonds can be alternative. So that means they have conjugated pi system. The alternating double bond represent the conjugated pi system. Right?
Yes, ma'am.
So this is also followed. Now comes the main rule which is present, Huckel's rule. Now, what is this Huckel's rule is? It is represented as 4n plus 2 pi electron, and the n value is a whole number or integer? It's a whole number, right? So this equation should be followed. So now let's see how many pi electrons are present in the benzene ring. So it has 2 over here, 2 over here and 2 over here. So that means 6 pi electron. So when I introduce 4n plus 2 equals to 6, my n comes out to be, how much does it comes out to be? Value of n?
1.
1. So which is a whole number? Which is a whole number, thus suggesting that it follows Huckel's rule as well. Had it been a fraction, then this Huckel rule is not followed. So that is why I can say benzene is aromatic in nature. It falls under the category of aromatic compound. Clear?
Yes, ma'am.
So if I try to see a compound which is not aromatic, let's say I have this. Now this compound will be aromatic or not aromatic. You need to tell me which rule is not followed. Okay? So can anyone tell me which rule is not followed? You have 4 rules. 4C basically: cyclic, planar, conjugated and Huckel rule. Does it follow all 4 of them, or does it follow only few of them, which makes it not aromatic, or does it follow all of them, makes it aromatic?
Ma'am, it doesn't follow
Huckel's rule.
Okay, let's try to establish how it does follow cyclic, planar and conjugation and does not follow Huckel's rule. So cyclic means it's a closed ring structure. Yes, it is. Planar means every carbon is sp2 hybridized. Yes, it follows. Conjugated system, this can be represented like this as well. So conjugated pi electron system. When I equate 4n plus 2 with number of pi electron present, what is the number of pi electron present over here?
4.
4. So your n comes out to be
Half.
1 by 2. So the Huckel rule is not followed. So this compound falls under the category of anti-aromatic. Okay, so we did aromatic, we did anti-aromatic. So the question has 3 different parts sometimes. So the aromatic compound, the Huckel's rule, when we study, we classify them into 3 different categories. What are they? Aromatic, anti-aromatic and non-aromatic. Okay, so let's see the third category as well. How is that third category? So let's say I've been given this compound. You need to tell me whether it's aromatic or not aromatic. You have to tell me only this. Then we'll make it fall under which category. Anyone?
Ma'am, it is not aromatic, ma'am, because it is not following sp2 hybridization every carbon.
Yes. So what is not followed? It is cyclic in nature. Yes, it is cyclic in nature. Secondly, it is not a planar molecule. It is not a planar molecule because this is sp2 hybridized, this is sp2, but this is sp3 hybridized. So this molecule is not planar. But it does follow Huckel rule. If you see over here, what it will be equal to? It will be equal to 2. Thus your n comes out to be 0.
0.
Yes, it does follow. So there comes the third category. What is the third category? Non-aromatic. Non-aromatic are those compounds which may or may not follow Huckel's rule. May or may not follow Huckel's rule. It doesn't matter. If either of 3 is not followed. If either one of them is not followed, then it is not aromatic. So what it is, it may or may not follow Huckel rule. Here in this case, it is following Huckel rule. In some cases, it may not follow the Huckel's rule. Then you might think that it's an anti-aromatic. But what you need to see, if the earlier three conditions are met or not. If either one of them is not met, then it is non-aromatic. Clear?
Yes, sir.
No doubt about it. So what exactly did I study over here? I studied the phenomena aromaticity. What does this aromaticity say? That the compound can be classified as aromatic if it is cyclic, if it has planar structure, if it has conjugated pi system, pi electrons, and it follows Huckel's rule. Then the compound is aromatic. Otherwise, there are two more categories which are present. One is anti-aromatic and the third one is non-aromatic. In anti-aromatic, what examples can I have? What is the rule? It is cyclic, definitely. It is planar. It has conjugated pi electrons, but it does not follow Huckel's rule. Right? And in the case of non-aromatic, so the three rules, that is cyclic, planar and conjugated pi electron is not followed, either two or all of them or either only one of them is not followed. Huckel rule doesn't really matter whether it follows or not follows. If either one of them is not followed, then it is non-aromatic in nature. Clear? Clear?
Yes, ma'am.
So there comes one exception molecule. We will be practicing more questions on the next class, but I wish to tell you about an exception molecule, and it is the most versatile one which is asked. So this is a cyclic structure of 8 members. Now you need to tell me whether this compound is aromatic or non-aromatic or anti-aromatic. First thing you need to tell me is this.
Anti-aromatic.
Okay. As per Ankit, it is anti-aromatic. What about rest of you guys? Okay, Reshma is also saying anti-aromatic. Why you are saying anti-aromatic? Because you say it is a cyclic structure, it is a planar structure as it is sp2 hybridized, has a conjugated pi electron, but Huckel rule is not followed because it comes out to be, n comes out to be 3 by 2. 3 by 2, right? That is what you meant?
Yes, ma'am.
But I am saying this is a non-aromatic compound. I'm saying this is my right answer and this is my wrong answer. Now let's try to understand why. This is an exception case. Why is it an exception case? In nature, this compound exists as a tub. So what do you mean by tub is it has a structure like this. Tub-like structure. So which makes it deviate from its planarity. Which makes it deviate from its planarity. So when the compound is not planar and whether it follows Huckel's rule or not follows Huckel's rule, that has to be non-aromatic. So this is an exception case. Why am I teaching you here? Because this is mostly asked. So it will be like the structure will be given to you and it will be asked identify the molecule as aromatic, anti-aromatic, non-aromatic, none of the above. 4 options are given. And most of the students who know the aromaticity and the root, they'll say it is anti-aromatic. But students should understand it's an exception, it's a non-aromatic compound because in nature it exists in the tub form. Clear?
Yes, ma'am.
So we'll see more exceptions. We'll see more exceptions in the next class and practice more questions based on this. Fine? So
Yes,
we're going to
ma'am.
stop here for today. Practice those questions so that you can understand it very well. Fine? Go through the notes and understand it. Thank you so much.
Thank you, ma'am.
ma'am.